And so, my children, we begin with a question, and the question is this. Is it possible for an object to be moving at a constant speed, but also be accelerating? Yes or no? And, oh, convince me. Can you be moving at a constant speed, but also be accelerating? What do you think? Nicky's thinking deep thoughts to himself. He's got a little smile on his face. Mr. Dewick, I thought you said constant speed meant you weren't accelerating. I never said that. Connor says yes. Convince me. There's two ways to change your velocity. Is velocity a vector, yes or no? Okay. So all vectors possess two quantities. They have magnitude, but they also have what? Direction. So if your magnitude isn't changing, that would be a constant speed, but your direction was changing, say going around a corner, you must be accelerating. And that's going to be the key to this entire unit. Technically, if I let you think about things for the next hour after that statement, I should be able to give you the test. Well, no, we have to do a lot more building. But the answer is yes. If you are changing direction, and a great example of that is moving in a circle. Now, we're going to move at a constant speed in a circle. There are some circles where you change speed as well. Let me just pause the video for 1 second. So, for an object, and here is going to be part of our key idea, we're going to be moving at a constant speed in a circle, or the fancy phrase for that, Ty, is uniform circular motion. Its velocity is changing, not because its speed is changing, Drake, but because its direction is changing. Oh, and if its velocity is changing, that was the definition of acceleration. Acceleration was a change in velocity over time. And if it's accelerating, there must be a force. This is the most important fact to keep about circular motion. The object is accelerating. But the acceleration, Nevada, is going to be different from your VF equals VI plus AT, A equals VF minus VI, your linear straight line acceleration. The second thing we want to talk about is the direction of the velocity. So here is my little circle analog right here. It won't rip, don't worry about it. If I were to cut this rope, for those of you at YouTube who can't see what's happening, on YouTube I'm whirling a ball on the end of a string around my head, and I'm trying to go at a pretty constant speed. Hopefully it's taking about the same amount of time to go around in one circle. I'm trying to eyeball it. I'm trying to feel it through my hand as best I can. But I want you to imagine that we froze this picture right here. If I cut the string so it moves around in a circle, and I slice the string right now, which way would this ball fly? Towards Andy or towards Duncan? Towards Duncan, but this is very counterintuitive. A lot of people think that when you're moving in a circle, say if you're on a merry-go-round in a playground, if you let go, you'll fly straight backwards from the center. And in fact, you're moving, your velocity is perpendicular to the center. We have a fancy word for that. We call it tangent to the radius. So, that's what I was trying to get across, Max, in this picture right here. If there's the radius, your actual velocity is tangent to the radius. And this is going to allow us to figure out the direction that you're accelerating. Now, I've told you that our bodies are backwards accelerometers, and so if you want to figure out what direction you're accelerating, it's always the opposite of which way you feel like you're getting pushed. So when you go around in a circle really fast at Playland, which way does your body feel like it's getting pushed? Outwards. So which way are you accelerating? Inwards. Here's the proof. Ready? To find the direction of the acceleration, we're going to do a vector subtraction. Acceleration is v final minus v initial over t but we're going to do vector subtraction. We're not just going to go with numbers like 5 minus 6. We're going to say now, because the direction is what's changing, we're going to have to bring some vectors into bear. Now, it's divided by time, but because time is a scalar, I'm going to say to you that the direction of the acceleration will be the same as the direction of this subtraction. It doesn't get any direction from time. With me, James? Let's do some vector subtraction. Oh, by the way, later on I'll be showing you that this acceleration isn't constant, and so this relationship is only true for a very small time interval. Those of you in calculus, we would say it's only true for a very small time value dt, or delta t. We would use a calculus approach to do this if we had the calculus background. But I want you to realize that this change in time won't change the direction. So on the next page, I have a vi, and then a little bit later, like a tenth of a second later, a vf. And we want to find the direction of the acceleration by subtracting vf minus vi. So vf looks like that if I eyeball it. Now vi looks like this. If we want to subtract vi, we don't. We add the opposite. We add the opposite. So what would negative vi look like? Instead of up and to the left, what? This is vf minus vi, and if I had lined this up really, really carefully, which I probably should have done, you can see, Robbie, it is pointing towards the center of the circle. This vector here is pointing to the center. If you're accelerating, and this is going to be the key concept, if you're moving in a circle, you're accelerating towards the center. Or if I want to make a generic statement, you're accelerating inwards. So, suppose you have a ball on a frictionless tabletop and it's rolled along a circular track as seen below from a top view. We're looking down at it. So we give the ball a push, it's rolling, it's rolling, it's rolling. When it gets to there, the track ends. What path will this ball continue on? Path A, due to the fact that the ball has some circular momentum and it wants to keep going in a circle. Path B, because when there's no force from the track, the object will go in a straight line, Newton's first. Or path C, since when the track is no longer applying a force on the ball will fly outwards, sort of like you feel when you're on a merry-go-round. What do you think? Yeah. But that's really tough to convince people of, because if they've been on a playground merry-go-round, they feel like they're getting thrown outwards, and so they feel like they're going to go shooting outwards, and I have to convince you that that's not the case. Why is the acceleration inwards? Turn the page. When the push that you feel, that you experience when a car goes around a corner seems to be outwards. The answer is it's not a push at all. What you're really feeling is your body's own inertia. It's an inertial effect. When you're turning in a car, your body wants to keep going in a straight line at a steady speed. That's Newton's first. The car moves this way, and what really happens is, for you to move this way, the car has to apply a force on you this way. Otherwise, your body would want to keep going in a straight line at a steady speed. Your head wants to keep going straight. The car applies a force to your body to get you to move around a corner. Your body feels that it has to pull on your head to keep your head with you, and it thinks to itself, oh, I'm getting pushed out. No, you're getting pushed in. It's your own inertia that you're feeling, wanting to keep going in a straight line at a steady speed. Your grandfather probably knew this. Ask your grandfathers. In the 1950s and in the 1960s, nobody wore seatbelts. And all the cars had bench seats, not bucket seats. The front seats were bench seats. And so if you were an enterprising young lad out on a date, you would get some surfer's wax, and you would wax down the passenger section of the front seat. And you would drive with your hand on the bench seat like this, and you would do a quick turn. You would do a quick turn to the right, and the girl would come sliding across to you, and you'd say, "Oh, hi, honey." Ask your grandfather. He may fess up to that. Now, that's not really what was happening. What was really happening was the girl was going in a straight line, inertia, and the car was moving underneath her. Okay? Put your pencils down, look up. I may sound like I'm repeating myself, but this is important. Many years of experience in cars, on amusement park rides, on merry-go-rounds, leads people to believe that there is an outwards force. In fact, there's even a name for this mythical outwards force. They call it centrifugal force with an F, and that's not a force. It's your own inertia, and the fact that you have to resist that inertia by exerting a force inwards. That's the force we're going to be talking about. But this outwards force isn't a force at all. It's inertia. It's your body wanting to, or the mass wanting to move in a straight line at a steady speed. Okay? Furthermore, vector analysis, which we've just done, shows us that the actual acceleration is inwards, and therefore the net force is inwards. If fighter pilots move too fast into a loop, they can become unconscious due to a lack of blood flow to the brain. People will say that the blood flowed away from their brain. This is sometimes attributed to centrifugal force. What's really happening? Let's gulp. Here's our airplane. And we're going to draw a fighter pilot in a chair right here. Okay? I'm going to represent the fighter pilot with a torso and a head, because those are the main things going on. Where is most of your blood located? In your torso. So the torso is full of blood and it's liquid. It wants to keep going in a straight line at a steady speed. That's Newton's first. But if the fighter pilot pulls up, what's going to happen? Well, now we're going to have his head, his torso, but the blood is going to be pooling in his feet. And he's going to feel lightheaded. We say that the blood moved down to his feet. That's not true. What actually happened is his head moved away from the blood. The blood stayed in a straight line, stayed where it was. But this is why fighter pilots can pass out if they accelerate in a circle too fast. Put your pencils down, look up. So how do we calculate circular acceleration? It's not Vf minus Vi over t. The proof is a bit long. I'm just going to give you the equation. Acceleration. But to distinguish this from our regular acceleration, I always put a little c for circular. The fancy word is centripetal acceleration, is equal to v squared over r, where v is how fast you're traveling around the circle, and r is the radius of the circle. By the way, this also explains why on a merry-go-round, if you ever, how many of you been on a playground merry-go-round before? Okay. Have you tried walking from the middle to the outside? Or if you try increasing the spin, if you spin it twice as fast, 4 times the force is required to stay in place because of the squared. Okay? For an object that's in uniform circular motion, constant speed, we can say that for an object making one complete loop around the circle, its speed will equal distance over time. We're going to say this. Circular speed equals circumference over time. I don't need to worry about acceleration. Now, we are accelerating in a circle because of the directional change, but we're not actually changing the speed, so I don't need to worry about bringing in a half AT squared or anything like that. Here's what this means. The equation for circular speed, so speed, don't write this down, just watch. It's distance over time. Circular speed, what do you call the distance around a circle? The circumference. What is the equation for the circumference? And then we call the time to go around once, we symbolize that with a capital T. We call it the period. That first equation, the acceleration equation, is on your formula sheet. Is this one on your formula sheet? I can't remember. Did I give you that V equals 2 pi r over t? Under circular motion? No. Is there a V equals? Okay. I just showed you how to derive it. I know there's one with a 4, but that comes in a second. A concept closely related to the period. So the period is how long it takes to go around once. A concept closely related to that is frequency. Frequency is the number of cycles in 1 second, the number of times you go around once in 1 second. We call this a hertz. 1 hertz is once around in 1 second. If you examine the units, period is how many seconds per cycle, frequency is how many cycles per second. They're reciprocals of each other. The period is 1 over the frequency, and the frequency is 1 over the period. And what that means, Drake, is if you know one, you know the other. Usually I'll give you the period of an object in seconds, but sometimes the information that you'll have is the frequency of an object in hertz. Turn the page. Suppose an object is moving at 4 meters per second in uniform circular motion. I underlined that. You can underline it again because this is the key. It accelerates at 2 meters per second squared for 3 seconds. A says, find the final speed of the object. I said to you folks that when you're moving in a circle, you have to unlearn certain habits. You might be tempted, don't write this down, to go, oh, Mr. Dewick, VF equals VI plus AT. That's for moving in a straight line. What type of motion are we doing? What did I underline? Here's what that means. It means V final is 4 meters per second because your speed's not changing. What's changing is your direction. And that 2.0 meters per second squared for 3 seconds, that's changing the direction of the object, not the speed. So that's one habit we have to really think about. What's the distance traveled? Well, the distance traveled is going to be speed times time. Mr. Dewick, shouldn't it be VIT plus a half AT squared? That acceleration is not changing the speed. It's changing the direction. You want to know how far it traveled? It went 4 meters per second. For 3 seconds, it traveled 12 meters. It accelerated, yes, but it didn't accelerate to speed up or slow down. There is no plus a half AT squared here. How do I know when to do that? If we're moving in a circle. And so one of the phrases you're going to hear me often ask whenever we're looking at these questions, I'll say, what path are we tracing out? And we'll all repeat back, a circle, and that'll put us into our mindset for circular motion, a little different from linear motion. Julie, there's a second equation for circular acceleration. I already told you that circular acceleration was equal to v squared over r. But I also told you that v, when you're moving in a circle, is equal to 2 pi r over the period. I can plug this into that v. When you do that, you're going to get, I guess, 4, 2 squared, pi squared, r squared, over t squared. That's the top part when you square the v. And then, Tori, in the original equation, there was an r already on the bottom, so I'll tuck that r down there already on the bottom. Oh! How many r's are there on the top? See the r squared? Is there also an r on the bottom? So this cancels out with this. Julie, this is that second equation that you were referring to when you said there's one that's got a 4 in it. Another way to calculate circular acceleration is like that, where r is the radius of the circle, and t is the period, how long it takes to go around once. Which equation do I use, Mr. Dewick? If they give me the period, if they tell me how long to go around once, or they ask how long to go around once, I'll use the 4 pi r over t squared. Pi squared, Mr. Dewick. Simone, is that what you were going to say? I spotted it. No candy for you. Simone, if they're talking about the speed, or they ask me for the speed, I'll use the v squared over r1. Let's summarize this. So, circular or centripetal acceleration equals v squared over r, or 4 pi squared r over t squared. Where t is the period, how long to go around once. R is the radius. And v is the speed, which they might tell you, or it's also 2 pi r over the period. So in uniform circular motion, we have a strange situation. The object is moving at a constant speed, but it's accelerating because its direction is changing. And the acceleration vector, the direction of the acceleration, is changing all the time. Here it's pointing inwards. Here it's pointing inwards. Here it's pointing inwards. Here it's pointing inwards. But the direction of inwards is different depending on where you are in the circle. So I can never say the acceleration is north or south or east or west. I always have to say, well, you know what? My fallback is going to be towards the center. If you tell me where we are on the circle, I can be more specific. But for now, it's going to be we're accelerating towards the center. What that means is we cannot use our constant acceleration linear equations. We have to use the equations for uniform circular kinematics. Circular acceleration is v squared over r, or 4 pi squared r over t squared, where v is 2 pi r over t. If we have to find a distance, it's just going to be the speed times the time. That's going to be the toughest one to unlearn, because you're going to say, well, there's an acceleration. Isn't it d equals vi t plus half a t squared? The acceleration isn't making it speed up or slow down. Another way to think about it is it's average velocity times time. So, let's apply some of these to some numbers. The Earth is currently rotating. Imagine that through some cosmic catastrophe, the Earth instantly stopped rotating, but those of us on the Earth maintained our centripetal velocity, our circular velocity. We would all go flying into the nearest wall due to our inertia. First question, which wall would we go flying into, north, south, east, or west? Floor is not south, that's down.
South is that way.
I'm going to give you a hint. I don't think it's the north or the south wall. It's either the east wall or the west wall. So would we go flying into the east wall, or would we go flying into the west wall? Things you've never thought about, but which you should. It's a great question. Which way does the Earth spin? You can figure it out, Connor. Please, God, help me. Please tell me you can figure it out. What? Oh, there's this big glowing ball in the sky, which looks to us like it's moving, but I know it's standing still, so maybe I can imagine which way I'm rotating to make the sun move a certain way. Okay. So they're thinking. What do you think? East or west? Which way does the sun move relative to us if we pretend we're standing still? This way. So the only way, if the sun is standing still, but it looks like it's moving this way, it must be because we are moving that way. Now, people on YouTube are going, this is really entertaining. What direction is that in my classroom, boys and girls? East. What direction are we moving? East. So if the Earth stopped, which way would we keep moving? Wow, that was painful. All right. If we were on the equator, how fast would we go moving into the wall? What's this question asking me to find? V. In a circle, VC equals question mark. Now the equation for circular speed is 2 pi r, distance, the circumference, over the period. 2 pi. You are going to want your formula sheet out for this entire unit unless you feel like memorizing all the radiuses and distances of the planets. On your formula sheet, on the page where I have all the data, I do have the radius of the Earth. What's the radius of the Earth? The period. What's the period of the Earth? You could also just say 24 hours times 60 minutes times 60 seconds. (24 hours times 60 minutes times 60 seconds). It's a bit of a problem here. It's not what it says on your sheet. Is it? What does it say on your sheet? 8.6. But I went 24 times 60 times 60. I got that. Have we been lied to? Is the Earth period not 24 hours? All right, I'm going to pause the video because I got to stand up. Sorry for you, those of you at YouTube. So what was the number from the formula sheet, Robbie? 80. 8.61 times 10 to the fourth? Okay. By the way, the reason I had to make this at the equator, because of course, as you move further north or further south, the radius of your spin does change. In fact, at the North Pole, really, you're just spinning like this. You would survive at the, part C, by the way, where would your preferred location on the Earth be if such a disaster were to occur? North or South Pole. What do you get here? 2. You want to find where your pi button is. You all have one somewhere. Times 6.38, scientific notation button 6, divided by. Is that right? You get 466 meters per second? Yeah. Times 3.6. About 1,700 kilometers per hour. It would be a pretty short. Wow, what happened? No one would survive. Well, sorry. Maybe at the Antarctica research station, and if there's a North Pole research station. Anyways, 466 meters per second. North or South Pole. Mr. Dewick is now going to go mention a little bit about angular or circular momentum and show you some cool demonstrations as well as an addictive toy. The exercises you can do, this is not for Monday, this is for next week, Wednesday, a week from today. I haven't covered every single little thing yet, and I'll talk about this Wednesday, but I'm curious if you can figure it out from the lesson. Number 1 is good. We'll skip 2. 3 is good. 4 is good. 5 is good. 6 is good. 7 is good but tricky. You'll have to think about it. 8 is good. 9 is good. 10A.